Well, so first of all, thanks for the nice invitation to give this talk. And so let me start saying that since I was not completely sure about the general background of the audience, I have prepared a talk which is more focused on motivation of problems and ideas than on calculations. Okay, but of course, if at some point you have any question about what I'm saying, I mean, feel free to ask. It will be a pleasure to answer. On the other hand, the price to pay for this more plain talk is that some people might find some of the first slides a little bit basic, but I think it's better to explain or to start from the very basic things. So that the motivation of the problem is clear, which I think is the most interesting part of the talk. Okay, so most of what I'm going to talk about is a joint work with Marius Junge, Alexander Kubik, and Ignacio Villanueva. And somehow the title of the talk, this quantum entanglement versus classical communication, could be understood in a more general sense. So what we wanted to do is to compare quantum entanglement, which is the key resource in quantum information, with classical resources, right? Whatever that means. And I will try to explain what I mean with that and why classical communication comes into play in this setting. Okay, so I'm going to start with something. Let me see, with something very well known in at least in part of quantum information, which are XOR games. Here I'm talking about classical XOR games because later on I will talk about quantum XOR games. But in general, one doesn't mention classical. So XOR games are what I'm going to explain here. Okay. So these are games where we have one referee and two players, A and B. So they usually refer to Alice and Bob. So the game is very simple. The game is that the referee is going to ask some questions to the player. So the questions are labeled with I and J. And the players are going to answer some possible outputs, which I'm going to restrict to +1 and -1. So they will receive a couple of questions, each of them a question, and they will answer one output. Okay, and now what we want to explain is which is how somehow the probability of winning the game, or whether we say that the players win the game. Okay, so let me explain the game in more detail. First of all, there will be a probability distribution over the set of questions. So the referee will ask a couple of questions, I and J, I for Alice and J for Bob, according to a certain probability distribution. Okay, and then once the players have received their questions, they are going to answer a +1, -1, each of them, and we want to decide whether they win or lose the game. So in order to do that, we are going to consider some coefficients. Cij, one coefficient, one sign for each couple of questions, so that if Alice receives I and Bob receives J and they answer A and B respectively, we will say that they win the game if and only if the product matches the sign. So in some sense, what we want to do is to be sure that the parity of the answers matches these signs. Okay, so there are two comments to make here. So first of all the information is known by all the people involved in the game. So Bob, Alice, and the referee knows everything about the game. The key point is that once the game has started, so once the referee has made the questions, the players cannot talk to each other. So Alice will not know which is the question received by Bob and the other way around. So they have to answer without knowing the other player's question. That is the key point. Okay, but what they could do is to agree on a strategy before starting the game, saying, okay, if I receive something, I will do something or whatever. Okay, and we want to know which is the probability of winning the game, which is the best they can do in order to win the game. It's clear that that will depend on the resources that the players can use. Okay, but in any case, there is a very naive strategy which is the following. Alice could say, okay, independently of what Bob is going to do, whenever I receive a question, I will answer 1 with probability half and -1 with probability half. And Bob can do the same. So you see that half of the time, because of the winning probability, half of the time they will obtain 1, the product will be 1, and half of the time they will obtain -1. So you see that with probability a half, they can always win the game with this very naive strategy. So this is the reason why when we are working with XOR games, instead of talking about the winning strategy of the game, we talk about the bias of the game. The bias of the game is the difference between the best or the largest winning probability they can obtain compared to this naive strategy, to this 1/2. Okay, this is just something technical, but it's like, and you see that we don't work with the winning probability, but something which is the bias. It's something between 0 and 1/2. Okay, so these are XOR games, and there are many reasons why XOR games are very interesting. They are somehow behind some of the applications of quantum information to quantum cryptography, to random number generators. But here, what I want to emphasize is that this context is very natural or very suitable to compare resources. So we could say, okay, if we allow the players to share some resources, let's say classical resources, we can study which is the best probability that they can obtain in order to win the game. Now, if we allow them to use some other resources, for instance, quantum resources, we could compute the same, and then we can see if using quantum resources, they can do better than using classical resources, for instance. Okay, so in order to do that, in general, we define a beta j as the largest possible bias when Alice and Bob are reduced to the use of classical resources. I will define that in a moment. And beta star j is the bias if they are restricted to the use of quantum resources. Okay, so what do we mean with classical strategies or classical resources? So classical strategies are those which can be written in the following way. So the probability of answering A and B, A for Alice and B for Bob, if they have received questions I and J, can be written in this way. Okay, so this is for every I, we will have a probability distribution in Alice part, and for every J, Bob will have a probability distribution there. So you can see that this is very basic. What we are saying here is that if they receive the couple of questions IJ, Alice will do something which can be written as a product of what Bob will do. So this is actually more than classical. This should be called local strategies. In general, classical strategies are a little bit more general. We allow for convex combination of these convex combinations of this kind of strategies. But since I'm not going to talk about classical strategies and they will not be very important in my talk, let me just define this. It doesn't change anything. So even if I would allow for convex combination, the value of the games that I'm going to use are exactly the same. So that doesn't help at all. So let me just define classical strategies as something which can be somehow split in this way, so that we have a probability in Alice's part times a probability in Bob's part. Okay, so now if we want to use or to define quantum strategies, these strategies are going to be those for which we allow the players to share a bipartite quantum state, so that we can think of a two-particle system, physical system, so that Alice has one particle and Bob has another particle. And then the strategy works as follows. So whenever they receive output I for Alice and J for Bob, Alice will perform a measurement so that the result of the measurements can be 1 or -1. And depending on what she obtains, she will output that, she will answer that to the referee. And same for Bob. Now, if you use quantum postulates or the postulates of quantum mechanics in order to see which is the probability of obtaining AB when they receive IJ, so you see that you will have a PUBM. So PUBM is just a set of operators, of positive operators summing up to the identity. You have to consider a POVM for Alice for every I, another POVM for Bob for every j. You will consider the tensor product because we are in a bipartite system, and then you have to consider the trace against the bipartite state that they are using. Okay, well, this is just a motivation to understand what I want to do, but we have two kind of strategies, two kind of probability distributions that they can obtain if they use different resources. And then one could see, well, we can try to compare these two types of strategies, which is better in order to play the kind of games that I'm defining. So there is a very famous game, which is the CHSH game, which is a game for which there are two possible questions per player. So at the end, there are 4 questions. So 1-1, 1-2, 2-1, and 2-2. Okay. Each pair of questions will be asked with the same probability. So we use the uniform probability. Each of the questions has probability 1 over 4. And then the signs which defines the winning probability or the winning condition, they are very easy. So if both players are asked question 1, then we assign the sign positive. So we assign a 1. And otherwise we assign -1. So that means that if Alice and Bob received question 1, they have to answer questions so that the signs are the same. And if they receive any other couple of questions, they have to answer some questions for which the signs are different. Okay, so you see that there is a very, very basic strategy in order to play this game, which is that, for instance, Alice will always answer 1 and Bob will always answer -1. If they do that, they will always get a product which is -1, so it will be 1 times -1. So unless the questions they have received are 1-1, they will win the game. Okay, so they will win the game 3 out of 4 times. It's just that for one of the questions they will fail. Okay, so it can be seen. This is a very easy strategy. It can be written as a classical strategy, and this gives you a winning probability which is 3 over 4, so that the bias, which is just subtracting 1 over 2, will be 1/4. It can be seen that this is the best strategy they can do is they use classical strategies. So this is the best winning probability if they use classical strategies. And in order to see this, that is very easy. A classical strategies can be seen as a convex set, and we have a finite number of extreme points. So we could check all the extreme points of classical strategies, and then you see that you cannot do better than 3 over 4. Okay, so this is the best they can do if you use those strategies, which can be written as a product of a probability distribution in Alice's part and a probability distribution in Bob's part. But it is not difficult to see that they can create a quantum strategy so that they obtain something slightly better. So if they use the maximal entangled state, they can use some measurements on Alice's part and some measurements on Bob's part. I'm not explaining here the measurements because it's not important in this talk, but you can believe me if I tell you that the winning probability is this cosine of p over 8 to the 2, so that the bias is approximate 0.35, which is strictly larger than the classical bias, which is 0.25. So we see that we have an example of a game, of an XOR game, for which quantum strategies are better than classical strategies, right? But there is a limitation with these kind of games. And it's like, if we complicate the games very much in terms of, for instance, considering many more questions for the players, or considering that the shared entangled state that Alice and Bob can use is not the one that I wrote here, which is just a 2-dimensional quantum state, but you use a d-dimensional quantum state with d as large as you want, the best that you can get if you consider the quotient between the quantum bias and the classical bias is always lower or equal a constant, which is strictly smaller than 2. So even though quantum entanglement can give some advantages compared to classical strategies, somehow the advantages cannot be very large in the sense that if you want to quantify this improvement of quantum entanglement with respect to classical resources, the advantages are not super powerful in some sense. Okay, so this is the motivation of what I want to tell you in this talk. So which is our goal? As I was telling you, our goal is to compare quantum entanglement or finding scenarios where quantum entanglement is better than classical resources. We have seen a scenario where we have somehow realized that that can be done, but there are some buts to what I have explained before. So first of all, it is not clear that classical resources should restrict to the kind of strategies that I have explained so far. One could argue that if you use classical resources, well, maybe we should allow Alice to send some information to Bob. So if I wanted to explain someone that quantum entanglement is much better than classical resources, I would feel much more comfortable if I can give some examples where quantum entanglement is still better than if they use classical information in order to play this game. Okay, so and the previous example doesn't or didn't use any kind of classical information. Okay, so in order to do that, we are going to follow the same approach. We will define those strategies which can be obtained if we allow Alice and Bob to share some classical information. And here we have to distinguish between two cases. We could allow for one-way classical communication, so we could allow Alice to send information to Bob, but not the other way around, or we could consider two-way classical communication, so that they can interchange the communication they want. But in any case, we will obtain some strategies which can be obtained if they use this resource, and that will lead to some bias, right? So whenever we have a game, we can compute the largest possible winning probability by using strategies, using one-way or two-way classical communication, and then we have the bias. And then we want to compare this with quantum entanglement. But there is a problem. If we use the previous games that I have defined, classical XOR games, you see that the questions from the referee to the players are classical. They were just I and J, okay, classical data. Then it's clear that if Alice can send some information to Bob, well, they could just say, well, whenever Alice receives her question, she could send that question to Bob, so that Bob can act as a single player, right? So Bob would have the complete information about the game because he would know both questions. And it's very easy to see that if in XOR games, if one of the players has access to both questions, the winning probability is 1. So they can always win the game with probability 1. So if we want to compare entanglement with classical communication, we should consider something more complicated than classical XOR games. We should consider something which, for the moment, I will call quantum games. And with that, I mean that at least there should be something quantum in the definition of the game. Because if everything is classical, with classical communication, you can always win with probability 1. Okay, here I have just written that for classical XOR games, the quantum bias, the B star at J, if you take the quotient over the one-way bias, both two-way or one-way, I have written that this is smaller or equal 1, but what I'm just saying is that the one-way bias will be always as large as it can be. So the winning probability will be 1, the bias will be 1/2, and of course, independently of the results that we allow, you cannot do better than that. The win is always, the game is always won with probability 1. So the first motivation or the conclusion of this explanation is that we need to define something more difficult than classical XOR games if we want to find scenarios where quantum entanglement is better than classical information. Okay? Second comment, we look for the simplest scenario. Once we accept that we have to consider quantum games, well, we could just define something very quantum in the sense that it is not surprising at all that if you use classical information, that doesn't help. Meaning that, well, we want to define a scenario where in principle we could think, or we could believe, that classical information will help, because if I define something ad hoc for which with classical information you cannot do anything, because everything is defined with quantum elements and you need to measure something in order to start playing, well, it's not so surprising that classical information doesn't help. What I mean is that I want to get a scenario where quantum entanglement is better than classical information, but the scenario should be simple. It should be something that I believe that classical information should help. Okay, because otherwise it is not surprising at all. And finally, we are talking about getting a better, something better with quantum entanglement, but better is not clear. Ideally, what we want to do is to find scenarios where quantum entanglement is arbitrarily better than classical resources. So if we want to quantify this comparison of resources by means of equation, I would like to find examples of games for which the value of the game, or the bias of the game, using quantum entanglement divided by the bias of the game using classical information, one way or two way, ideally two way, because that would be great, that tends to infinity. So in some sense, the advantages go to infinity, right? So it's not just that you have a scenario where with using quantum entanglement you can do slightly better, but in principle you want to do, or you want to say that you can do much better. So if we got all these things, we would be really saying, okay, quantum entanglement is much more powerful than classical resources. Even if you allow classical communication, and it's much more powerful in the sense that the quotient can be very large. Okay, that is what we are looking for. Okay, so what I'm going to use here is something which I will try to convince you that is somehow natural as a first step, which is considering quantum XOR games. So it's a quantum version of classical XOR games. And these games were defined by Oder Regev and Thomas Vidic, somehow with the motivation that since classical XOR games are so important and so interesting in quantum information and also in computer science, well, one could expect that if you use or you define a quantum version of that, that could be very useful also in these fields. And if in addition you get something in the quantum case that you don't get in the classical case, that would be great. That gives you like a wider context where you have to, or when you can work. Okay, so quantum XOR games are pretty similar to classical XOR games. The only difference is that the questions from the referee to the players are going to be quantum. That means that instead of asking a question I to Alice and a question B to Bob, J to Bob, sorry, the way the referee asks the question is going to be the following. They prepare a bipartite state and they send register A to Alice and register B to Bob. Okay, so here you can see that there will be n questions, but the questions will be identified with bipartite state. Okay, so that each question is just that the referee asks this state to Alice and Bob, sending one of the particles of the state to each of the players. Okay, the rest of the game is going to be exactly the same. We will have a probability distribution over the set of questions, a probability distribution to decide which state we want to share. In order to decide whether the players win or not, we will have a set of signs. Now the questions will be given by bipartite state. This is the only difference, but the winning probability is exactly the same. If the players has been asked the question indexed by psi I, and they have answered certain outputs AB, which are +1 -1, they will win the game if the parity matches the signs. Okay, so it's exactly the same. Just note that here I don't have to use I and J because the questions are indexed by quantum states. Okay, it is very easy that classical XOR games are a particular case of quantum XOR games. It's very easy to see how to reproduce a classical XOR game by quantum XOR games just using some states which in particular are orthogonal. Okay, and they can be distinguished very well. Okay, so why am I using this game? Well, first of all, if classical XOR games are somehow the most simple classical games, well, one could argue that if you want to go to the quantum case, quantum XOR games somehow the easiest quantum games. Okay, at least we don't have quantum answers. And we know something, certain things very interesting about these games. So first of all, Regev and Vidic proved that there exist some quantum XOR games for which if you compute the quantum bias and you divide over the classical bias, then that is larger or equal square root of n. Recall that I have told you that for classical XOR games, this quotient is always smaller or equal than a universal constant. So it cannot grow to infinity. While here, if you increase certain parameters of the games, you can have large advantages. Okay, so in principle, this is very good for us because, well, if we want to find something for which quantum entanglement is much better than classical resources, well, this result doesn't prove what we are or what we want to prove, what we want to get, but at least it tells us that quantum entanglement is much better than at least classical strategies in the sense that I defined it before. Okay. Okay, so let me tell you, although this is not very important in what I'm going to tell you. So let me tell you how this game works. Okay. So for every natural number n, the quantum game that I'm going to define has only two possible questions. Okay, so I am going to index I from 1 to 2. One question, which is one of the state, is given by this state here, which is in dimension n+1. You see that you have n, so the canonical base or the computational base goes from 0 to n. So you have dimension n+1, and you have the second state, which is exactly the same up to the point that instead of having a plus here, you have a minus here. So you have these two states. So the probability distribution is going to be the uniform. So with probability half, the referee asks the first state to the player. So that means that the referee sends the first register to Alice and the second register to Bob. And with probability half, sorry, the referee will send the second state to the players. Okay. And now what they have to do is to distinguish the states, because it's clear if we only have two questions, the only possible coefficients that we have to, or that we can have, is 1 and -1, right? So they have somehow to distinguish between these two states, right? So if you look at this state, you see that the states are orthogonal. These are two orthogonal states. So one could think, well, but if they are orthogonal, then they can be distinguished. There's no problem with that. But have in mind that in order to distinguish these two states as orthogonal states, we should apply something global in both registers, while Alice and Bob will not be able to do that. So once they have received one of these states, Alice will act on one of the registers, so one of the state of one of the particles, and Bob will act on the other particle, right? So it's not, in principle, it's not easy for them to distinguish between these two states. Okay, in fact, you can see that if you use classical strategies, the best you can do is to get a bias which tends to 0 as n goes to infinity. Okay, this is not difficult to see, but the interesting point here is that you can actually prove much more than this. You can prove that if you restrict to quantum strategies, but the bipartite state shared by Alice and Bob is the maximal entangled state, you get the same bound. Okay, so either if you use classical resources or you use maximal entangled state, you get this bound, this upper bound. Right? This is unequal, but I care about the upper bound. On the other hand, you can see that the quantum bias, so if they can use an entangled bipartite state in order to answer this game, they can obtain a bias which is half. That means that they can win the game with probability 1. So with quantum resources, with entanglement, this game can be won with probability 1. But if you restrict to classical strategies, and with classical strategies, I'm not allowing classical information, but classical strategies, the winning probability is very low. It tends to 0. Okay.
Carlos,
Yeah.
what you referred to as the classical strategies, the players still have to perform quantum operations, right? They have to do measurements.
Definitely, that is a very good question. In 2 slides, I'm going to write certain things, but yeah, I mean, Job's question is very interesting. It's not clear what classical strategies are here. So with classical strategies, I'm meaning an entangle strategies. So I'm meaning that Alice will receive a particle, Bob will receive a particle, and in order to answer, Alice will apply a measurement on her system, and Bob will apply a measurement on his system, but they cannot do anything mixing the systems. Okay. So just, I mean, the definition is very easy. So have in mind that whenever Alice receives one state, let's say that so Alice and Bob receive this state, okay? Alice has to answer 1 or -1. Bob has to answer 1 or -1 So the strategy is going to be given by Alice applying a POBM with two possible outputs in her part of the system, and Bob will apply another POBM on his part of the system. That is an entangle strategy. It is just that they cannot share another state in order to mix things. Is that clear what I'm saying? So just have in mind that this state is in HA tensor HB. So an entangle strategy, which I'm calling classical strategies, is just that Alice applies something on the first Hilbert space, and Bob applies something on the second Hilbert space. And then we consider tensor product. I will write something mathematically later, but it's a good question, because indeed there is a gap between classical XORs and classical and quantum XOR games. Okay, so let's talk about an entangle bias and entangle bias. An entangle bias is Bj, and entangle bias is B star J. Okay, is that clear? Great. So the question is clear. So these games look very promising in order to prove what we want to prove, right? So these games are at least games for which the questions are quantum. So it's not clear at all that classical communication can help, because well, it's not clear in the sense that at least you cannot trivially send something from Alice to Bob or the other way around, so that you can assume that one of the players has access to both or to the whole question. And second, we have seen that these games allow, or there are some examples of games for which quantum entanglement is much better than classical entanglement, right? So, so they are promising. So the question is, can we use quantum XOR games to find examples where entanglement is much better than classical information, one way or two way? And somehow the theorem that this is like the result that I wanted to present is that it is surprising that you cannot. At least I would have said that using classical information is not enough to do whatever you can do with entanglement. So I would expect that for these games where the questions are quantum, entanglement could be much more powerful than using classical information. Okay, so the theorem says that the opposite. So there exists a constant, let's say 10, I will tell you the constant we get, such that for every quantum XOR game, the quantum bias of the game is smaller or equal than this constant times the classical bias. So up to the constant k, this says that whatever you can do with entanglement, you can do it with classical communication. Okay, one has to be careful with the constant, because we don't get constant one. I will tell you something about that. But what I'm just saying is that even though the questions are quantum, even though quantum entanglement can be much more powerful than unentangled strategies, if you allow the players to use one-way communication, the quantum bias is smaller or equal the one-way classical communication up to a constant. Okay, so for me that is surprising. So the answer is no. Quantum XOR games are too simple. You cannot use these kind of games in order to find examples where quantum entanglement is much more powerful than classical resources, if classical resources involve a classical communication. In fact, one way is enough in order to get the quantum value. Okay, so let me make some comments. So first of all, this is an inequality in one direction. Obviously, we cannot expect the inequality in the other direction. We are not saying that the quantum bias is equivalent in some sense to the classical bias with one-way communication, because, as I have told you before, classical games are a particular example of quantum games. And we can find classical games for which classical information is much better than entanglement. Okay, so if there are classical games for which the classical bias with one-way communication is much larger than the quantum bias, in particular, you have quantum games verifying that. So there are some examples for which this is much higher than this. Okay, so we cannot expect a converse inequality in any sense. Okay, second point, we got a constant, which is this one that I wrote here. It's not optimal. We didn't make an effort to optimize the constant, but the techniques that we used in order to prove this theorem will not lead to constant one. So we don't know if you can get constant one, and that is a question. So can you get constant one in this inequality? That would mean that whatever you can do with quantum resources can be done exactly, at least, with one-way classical communication, in the sense that you don't have to pay anything. Here, if the constant is larger than one, in principle, you could find some quantum games for which, with quantum entanglement, you can do slightly better than with one-way classical communication, because the constant is not one. We don't know if the constant can be one, but we don't know how to prove it. Okay? In any case, it is interesting to say that if you remove the XOR condition from the game, that is, if you consider quantum games for which you define exactly the same as I defined it before, but the winning condition is not restricted to the parity, but you define some other more complicated conditions, there are some examples for which the quantum value is strictly larger than the one-way classical communication. So what I'm saying is that even though we don't know if K can be equal 1 in our theorem for XOR games, there are very basic games with only 2 outputs, but they are just not XOR, for which the quantum value can be strictly larger than the one-way. So I don't know if finding or studying if the constant can be 1 or not is a super interesting problem. Okay, because if you remove the XOR condition, but you are still in a very, very simple way, you have some examples where you can find that quantum entanglement is strictly larger than one-way, but it cannot be much larger because of this theorem. Okay, so the current research that we are doing now is somehow still finding or still looking for nicer scenarios where this can be arbitrarily large. So our point was that well, with quantum XOR games, maybe we could find that, but we couldn't. So we are now studying in what sense or in what context we can find examples for which the quantum value is much larger than the classical value with two-way communication. We have some examples, but we are studying, like is what I was telling you. We want to find somehow the simplest scenario where you can have that phenomenon. Okay, so this is more or less the results I wanted to tell you about. And then maybe the next 2 slides are going to be a little bit more technical, because I wanted to give you not the idea of the proof, which is it uses a lot of functional analysis, but at least the idea of which are the elements that we use in the proof. Okay, so the first that I'm going to tell you is, okay, we have talked about a bias, so classical bias, quantum bias, one-way bias, but we haven't written anything. So let me tell you how you can write things, okay? So first of all, well, I have defined a game, a quantum game, and here I define it like saying, okay, the referee asks some questions, the players answer something, but then at the end, what you want to do is to define a mathematical element so that you can compute things on that element, okay? So once you have a quantum XOR game, if you define this element, this is just a metric. So for any of the states which define the question, you consider, well, the state, not the pure state, but the density matrix. Okay, you put this -1 CI where you are putting the information of the coefficients that you will use in order to define the winning probability. And here you add the probability distribution of the question. So then you get an element which you can see that is in Mn tensor mm, okay, and that is a big self-adjoint matrix. Okay, so this is important because what we want to do is to define an element for which we can compute things. So the key point is that if you are working with quantum XOR games, this element, if you want to compute the bias, this element has all the information that you need to use in order to compute the bias. This is exactly in the same way as you do in the classical XOR game. You define a classical XOR game by means of the instructions and these kind of things. But then from that, what you do is to define some coefficients that they are usually indexed like T sub ij, so that you can compute things on these coefficients. Okay, so here is the same, but in the quantum case, we don't have coefficients, but we have an element in the a matrix. Okay, so we have this matrix, which is a self-adjoint matrix in n tensor m, and it's very easy to see that this matrix has the property that the trace norm is smaller or equal 1. This is very easy because if I want to compute the trace norm of this, I want to compute the trace norm of this. I use the triangle inequality so that I can put the trace norm here. The -1 is not seen by the norm. The pi is a probability distribution, so it will not play any role. And then you see that the trace norm of a state is 1. So it's very easy to see that at the end, the trace norm of G can be upper bounded by the sum in I, the probability distribution times 1. So it will be always smaller or equal 1. In fact, it can be seen that any self-adjoint matrix so that the trace norm is smaller or equal 1 defines a quantum XOR game. For any of these metrics, you can get some states and some a probability distribution and some coefficients so that you have a quantum XOR game. Okay, so there is somehow correspondence between self-adjoint matrices of norm lower or equal 1 with the trace norm and quantum XOR games. Okay, now if we want to compute or to write the bias of the game, the classical bias, what I was saying, or the unentangled bias, this is what I was saying. So you have this game, which is representing what Alice and Bob will obtain in a tensor product of two Hilbert spaces, and you will have to do something in Alice's part and something in Bob's part. In principle, what I was saying is that if you want to define the probability distribution of the answer, you will need to put here, or you would need to put here a PUBM for Alice and a PUBM for Bob. Since we are talking about computing the bias, instead of putting the PUBM, you have to write for any PUBM the projection associated to output 1 minus the projector associated to output -1. And this is the reason why in Alice's part we obtain these operators, which are operators. When I write S infinity n, what I'm meaning is that Mn with the operator norm. When I write S1n, I write Mn with the trace norm. So these are the ones, okay? So here I'm just writing a self-adjoint operator with operator norm smaller or equal 1. And you can see that that is coming from considering a projector associated to 1 minus a projector associated -1. But anyway, I mean, I think that this slide is clear if you have worked on this. If you haven't worked on this, the only thing that you have to understand is that the classical or the unentangled bias is just the element which is representing what Alice and Bob are going to obtain, and then you will have something acting on Alice's part, tensor, another operator acting on Bob's part. Okay. Now, if you want to understand the entangled bias when they can use entangled states, you will have the following. So you will have this J, which is the information telling you what Alice and Bob obtains, and then we have another state which is going to represent the entangled state shared by Alice and Bob. So now you see that Alice has access to the A part of this system and A prime, and Bob has access to the B part of this system and B prime. So you see that now it's exactly the same as before, but you have just tensorized the game with the entangled state, and now the action of Alice is an operator acting on both N and D, because it's acting on the first part of the system here and on the first part of the system here, and same for Bob. So you can see very easily that the quantum or the entangle bias is going to be definitely larger or equal to an entangle bias, because if you don't use this, you obtain exactly this. But in principle, you can use an entangle state which allows the players to mix things, in the sense that they can somehow transfer some information. Okay, that is the magic of quantum entanglement. Okay, and now if you want to understand the classical bias with one-way communication, this is a little bit more tricky, and I just give you an idea about how to do it. So the thing is very easy. So think about what they are going to do. So once Alice has received her part of the system, her part of the question, she will have to perform a measurement to decide two different things. She has to decide the output that she's going to output, so that she's going to answer, and she has also to decide, she also has to decide the message that she will send to Bob, the classical message. So at the end, Alice's action is going to be given by a big POVM acting whose outputs are the output of the game and the message that she's going to send to Bob. Okay, and on the other hand, Bob's action is going to define, or it's going to depend on the message received by Alice. So for any message, for every classical message, she will be able to decide what measurement or what POVM he applies. Okay, so at the end, if you write the bias, you obtain that you have to somehow sum over all possible messages that Alice can do, and for each of the messages we have something very similar to the classical case. So Alice will do something, okay, which is as before, this is a self-adjoint operator with operator num lower equal 1, and depending on K, Bob will do the same. Okay, well, this is a little bit rough, but I was not able to explain it in more detail, I mean, without writing in a blackboard. And let me also say that here I have simplified certain things. For instance, if they are using classical information, well, we should allow them to use shared randomness as we allow in the classical case, but it can be seen that shared randomness doesn't help and this kind of thing. So I'm just saying that I have simplified a little bit the expression. So the expression could be a little bit more complicated, by, in some sense, it is equivalent to what I have written here. Okay, so finally, we have written things in a mathematical way. Great. But there have been different works. What we have done is to write like a physical problem to translate into a purely mathematical problem, mainly using norms or tensor norms or norms on operators, and then trying to identify certain norms which are known in functional analysis, so that they are the same or they are equivalent to the quantum or to the physical quantities that we want to study. So as I was telling you, if you look at a quantum game in this way, so as a self-adjoint matrix in Mn tensor MM, you see that algebraically these elements can be identified with linear maps from Mn into Mn. Okay, I'm just using that. If you have an element in X tensor Y, you can always identify that algebraically as a linear map from X to Y. Okay, then it can be seen that if you compute the classical bias, this is up to a constant 2, or this coincides with the norm of this linear map if in the first space here you put the operator norm, and in the second space you put the trace norm. Okay, so we identify the classical bias as a norm of a linear map. And what I'm saying that we identify, in some sense, I mean, in some cases, it is completely trivial. So if you write what the classical bias means, and you write what this norm means, instead of taking the supremum over the unit ball of the first space and these kind of things, it's something very, very basic. This approx is just because the classical bias is defined via self-adjoint elements, while if I write the norm of an operator, there's no self-adjoint at all. So, so you have to pay a 2 a constant 2 so that you pay so you convert any metrics into a self-adjoint matrix. But apart from that, for instance, this approach is very easy. I mean, it's just writing the definition of this norm. Okay. In fact, you can always, you can also see, and I'm finishing my talk now, that the quantum bias is actually the norm of G when you see it from S infinity to S1. But now you have to consider another norm here, which is called the completely bounded norm. So I have written here what the completely bounded norm means. Okay. And it's just that in some sense, I'm not going to explain this into much detail, but it's the same spirit as passing from positive to completely positive. So if you have a positive map and you want to study if it's completely positive, you tensorize the map with the identity and you see that, or you want to study if the extended map is completely positive. So here is somehow the same. You can compute the norm or you can compute the completely bounded norm. The completely bounded norm is just to consider G, tensor identity, and put it in another space here and studying the norm of operators. It's just that in order to understand this completely bounded norm, here I'm cheating a little bit because I should explain which these norms are, and I'm not explaining this, but I mean, this is not important. The important thing is that the quantum bias is exactly a norm which is very well known, in functional analysis, right? And the third point is that we could prove, here, we could prove that, here. So we could prove that the one-way classical communication can be identified with another norm, which is a little bit more complicated. But again, it's a little bit more complicated because the expression for the one-way is complicated. But if you write what I have, so if you know the definition of this norm and this norm, and you write the norm that I have written here, is pretty similar to the expression that I have given you for the one-way classical communication. So the norm is more complicated, but this is just because the expression of the bias with one-way classical communication is more complicated. There is this sum in K and these kind of things, okay? But once we could express the one-way by means of a norm that we know more or less well in functional analysis, the main theorem that I wanted to tell you, or that I have told you before in the context of quantum XOR games, is that we could prove that the completely bounded norm is upper bounded by a constant times this second norm. Okay, key tool, non-commutative Grothendieck theorem. One can have some expressions for the norm where a non-commutative version of Grothendieck theorem applies. I don't know, I mean, first of all, I don't have time to explain the proof in detail, but in fact, we were very frustrated because once we knew the result, at the end, we should be able to find like a constructive way to prove this, right? So what we are saying somehow is that if whatever we can do with quantum entanglement, we can use it we can do it with classical communication. But at the end, if you give me a strategy using a quantum entanglement, I should be able to give you a strategy which, up to this constant, using classical communication makes the same. But we cannot do that. So the mathematical proof that we have is based so much in non-constructive arguments, not difficult, but non-constructive in the same of, so in the spirit of Hahn-Banach theorem or things like that, that we cannot, or we don't know how to proceed in order to give a protocol using one-way classical communication, which gives the same as the one for quantum, okay? Well, we didn't have a super strong motivation for that. So anyway, we didn't try so much, but I'm just saying that it is not trivial at all extracting from our proof something which is constructive in the sense of quantum information. We didn't know, we didn't try so much, but it's not easy. Okay, so I think that I will finish the talk here. I had something just to give you in 30 seconds. The good point is that once you have defined or you have identified some values for games with some norms, you can use some other result, or you can develop some other results in order to study some mathematical question. For instance, you could say, okay, if I sample a quantum XOR game at random, which is the typical behavior of that game, okay? First of all, how do you sample something at random? Well, once you know that XOR games can be identified with self-adjoint matrices, there are different natural ways to sample self-adjoint matrices. Okay, this is super well studied in random matrix theory. And you can see that if you sample something at random, the expected value of the classical bias is up to constant the expected value of the quantum bias or the entangle bias, which is order n squared. The expected value of the one way is a square root n larger order from the classical and quantum. And of course, you could compare the global the global behavior. When I'm writing here global bias, I mean that the players act as a single player. Okay, so they have access to the whole information, and you can see that the order is larger. Okay, so this gives you an idea about typically how quantum games behave in terms of the different strategies that we can use. Okay, and I think that with this I finished my talk. So thank you very much. I thought it was shorter, but